In the last two videos, we saw the derivation of four Maxwell's equations. I have written all the four in this slide. The first one, which we derived from the internal energy U, the expression for internal energy U is dou T by dou V at constant entropy is equal to minus dou P by dou S at constant volume. The second equation which we derived based on enthalpy is dou T by dou P at constant S is equal to dou V by dou S at constant pressure. The third, which we derived based on Helmholtz free energy, is dou P by dou T at constant volume is equal to dou S by dou V at constant temperature. And the fourth one, which we derived based on Gibbs free energy change, is dou S by dou P at constant temperature is equal to minus dou V by dou T at constant pressure. Okay. The first two equations have a negative sign, whereas the second and third are positives. Okay. If you look at these equations carefully, if you know one equation, you can write the other three. For example, if I am by hearting, dou T by dou P at constant entropy is equal to dou S by dou V, dou V by dou S at constant pressure, then I can write all the other three. How do I write the third one? Just inverse this term and inverse this term. Then the factor which is on the denominator are kept constants. Okay. And what about the first equation? The first equation is cross multiplying this equation. This equation is cross multiplied, dou S by dou V, and the second equation dou P by dou S at constant pressure. The denominator terms have been kept constant. Here it's dou V, so here it's V constant, here it's dou S, hence S constant. We are putting it a negative sign for the first equation as well as the last equation. So what about the last equation? The last equation, take the third equation, cross multiply dou S by dou P and dou S by dou P. Dou S here, dou P is taken to this side, cross multiplying, and here dou T by dou V, dou S, dou P. Take dou V here, dou V by dou T. When you cross multiply and get an equation, you can put a negative sign. Thus we can remember all the four equations if you by heart one equation. And if I am by hearting this equation, this is how you remember the other three. You have other ways, ways to remember these equations, like Maxwell's triangle. If you search in Wikipedia, you have so many ways to remember these equations. Okay. So what is the point in remembering all these equations? Okay. Now let's see what's the point. What is the significance of these Maxwell's relations? These Maxwell's relations can be used to derive other important equations such as Clapeyron equation, thermodynamic equation of state, etc. There are so many equations that use Maxwell's relations in their derivations. A few has been mentioned here: Clapeyron equation, thermodynamic equation of state. Okay, so remembering Maxwell's equations helps us in deriving other thermodynamic equations. The second significance is that certain experimental quantities which are difficult to be measured experimentally can be determined by making use of Maxwell's relation. For example, to find the variation of entropy with volume, we have to measure the change in entropy of a system with respect to volume at constant temperature conditions. It's very difficult to measure entropy, and to measure change in entropy is also difficult. So what do we do? According to Maxwell's relation, dou S by dou V at constant temperature is equal to dou P by dou T at constant volume. So if we measure the change in pressure with respect to temperature of the system at constant volume, then we can determine this. So for a system which keeps changing its volume at constant temperature, to determine the change with respect to temperature at constant volume is also difficult. In that case, we have another method. There are two terms, coefficient of thermal expansion alpha and coefficient of compressibility beta. Alpha is 1 by V. Alpha is defined as 1 by V into dou V by dou T at constant pressure, and beta is 1 by V into dou V by dou P at constant temperature. Okay. Then minus alpha by beta from this definition is equal to dou P by dou T at constant volume, and dou P by dou T at constant volume is dou S by dou V at constant temperature. Thus, by knowing minus alpha by beta, alpha and beta being constants for any substance, alpha is coefficient of thermal expansion and beta is coefficient of compressibility. These two terms being known, these two constants being known, we can determine the change in entropy with respect to volume at constant temperature of a system without any experimentation. Okay, that's the beauty of Maxwell's relations. Okay, another useful relation is dou S by dou P at constant temperature, the change in entropy of a system with respect to pressure at constant temperature, and that is equal to minus dou V by dou T at constant pressure. Okay, this is P. Okay, and that is equal to, from this definition, that is equal to minus alpha into V. Thus, by knowing alpha, the coefficient of thermal expansion, and multiplying it with volume of the system, we can determine the change in entropy with respect to pressure at constant temperature. Thus, Maxwell's relations are significant in determining quantities which cannot be determined experimentally. But these 3 points denote the significance of Maxwell's relations.